I will first introduce the journal for those of you who may not know the details. So, as you can see here, the journal Annales Henri Poincaré started in 2000, but it's actually a much older story since it is a result of a merge of two much older journals, Helvetica Physica Acta, edited by the Swiss Physical Society and published by Birkhäuser in Basel, starting in 1928, and the Annales of de l'Institut Henri Poincaré in Paris, published by Gauthier Villard since 1930, who once changed the name because the journal split in several sections. And these two journals merged in 2000 to give birth to the new journal. So what is important to know is that Annales Henri Poincaré is a non-profit organization. It is an institutional organization. The journal is co-owned by the Swiss Physical Society and the Institut Henri Poincaré. And as such, its only purpose is to serve the community. And it does that in several ways. But for example, he is financing the participation of young researchers in conferences. And for that, organizer of conferences just have to send an email to the editor-in-chief, and then he will tell you if it is possible or not to get the support. And the second way is the reason we are here today is this Annales Henri Poincaré Prize that is given every year to the best paper of the year. It consists of 3,000 euros to be shared among the authors of the best paper. This paper gets open access in the journal for 1 year, and the authors get the opportunity to present their work today, so at the next ICMP. And today I should also mention that AHP is one of the main sponsors of the present conference. So, okay, so for today we have three winners to honors. So the 2017 prize was given to the complexity of translationally invariant spin chain with low local dimension by Johannes Bausch, who will do the presentation today, Toby Kubitz and Maris Ozels. In 2018, it was Universal Recovery Maps and Approximate Sufficiency of Quantum Relative Entropy by Marius Junge, Renato Renner, David Sutter, who is here, Mark Wilde, and Andreas Winter. And last year, the prize went to an autonomous quantum machine and finite size clock by Misha Woods, who is here, Ralph Silva, and Jonathan Oppenheim. So I will now call Jan Holland from Birkhäuser, our publisher, and he will give the medals to the winners. And so the two present winners can also join here in the. Okay. Okay, so we'll start with the first talk this afternoon. So Misha Woods will present his work on autonomous quantum machine and finite size clock. Just a few words about Misha. He did his undergraduate studies at Imperial College. He did his PhD jointly at Imperial College, and then he moved to Ulm University. Then he got a joint postdoc in Singapore at the Center for Quantum Computing and at UCL in London. And he's now at ETH as a postdoc, soon to be finished. And he will join INRIA in France next year. So please, Misha.
So thank you for the very kind introduction. Can you all hear me, or should I speak into this? Maybe that's a bit better, right? So yes, as I was saying, thanks to all the organizers and the editors for choosing our work. We are, all three of us are very grateful. It's a shame that the other two authors couldn't make it today, but I'm sure they would also have liked to be here had the circumstances been different. Okay, so without further ado, let me present our work. So first off, I have to, how does this thing, oops, no. I think one of them is meant to be a pointer. I have to, okay, it's, seems to have a little bit of a mind of its own. Okay, technology seems to be going backwards. The old-fashioned laser pointers looked, aimed where you pointed them. But okay, we'll have to make do with what's available. So the outline of the talk will be as follows. So we'll first off talk about so-called idealized clocks and control. And here the point is that these objects are very simple. They have lots of nice properties, but they are unphysical. So then the next section of the talk will be about quasi-ideal clocks, which is the contents of the paper that won the prize. And here, basically, the aim is to design finite dimensional clocks which mimic the nice features of these idealized clocks, but without the bad features, so to make them physical. And then, if time permits, we'll give some examples of applications in quantum information theory of these results. Okay, so the story starts way back with Wolfgang Pauli, who asked, does there exist a perfect clock in quantum mechanics? i.e., is there a self-adjoint operator T and a Hamiltonian H such that in the Heisenberg picture, the derivative of this time operator with respect to time is just the identity operator? Because this would be then analogous to like time in quantum mechanics would be like an operator. And he concluded that the answer is no, since the only solution up to unitary equivalence would be that the T operator is the position of a free particle in one dimension, and the Hamiltonian will be the generator of translations. And the reason why he said no is because while this solution is mathematically perfect, or at least can be well defined, the Hamiltonian has no ground state. So therefore, hence, it's unphysical, and maybe you need like infinite energy. So some of Pauli's critics pointed out that later on, when the maths of quantum mechanics was more developed, people pointed out that he missed a solution to the equations, namely that he only considered generators of Weil pairs, whereas you can consider the more general type of commutation relation known as the Heisenberg by in the 1970s. However, here, while the actual Hamiltonian now is bounded from below, so you have a ground state, you do need these infinite, you do need strict confinement of the wave function, which requires these infinite potentials. So many then critics to this work say, well, you're just hiding the energy in these infinitely strong, infinitely deep potentials. So, but if you could achieve such a thing, it would be very useful, as we'll now show. So, as many of you are probably aware, if you look at the wave function at time t of such an object, then a translation in time by the amount t is just a translation in space. So we have this rigid translation. So apologies, I did want to kind of point with the laser pointer while I was talking, but it doesn't seem to be functioning. But I hope when it gets a bit more complicated, you'll still be able to follow me. Okay, so that's that. what happens now if we add a potential to this Hamiltonian, so some smooth function evaluated some position operator. So now we see that a translation in time also gives a translation in space, but now we acquire phase, which is the integral over this potential that we've passed through, okay, so as the diagram below indicates. So here, there already seems to be something a little bit which may seem unphysical, which it appears that there's no back reaction, in the sense that this potential is going through this, this wave function is going through the potential, but with perfect rigid translation. It doesn't feel any kind of interaction or reflection from this potential. And now we'll say why these kind of objects could be very useful in practice, though. So a very elementary thing you want to do in quantum information theory is you have some, say, finite-dimensional system and some state, and you want to apply unitary US to it. So at some time t0. So we can write this unitary in the form of some Hamiltonian h int, as shown here. And then we can construct a time-independent Hamiltonian on the clock system and on this system we want to apply the unitary to as follows. And now if we start the initial system clock state as a tensor product state, where the initial state of the system is the state we want to apply the unitary to, we find that solution is as follows. So again, we have a translation is time, it's just a translation is based on the wave function, but now the phase is a bit more complicated because of the interaction term, and we see we have this term acting on the system we want to apply unitary to. And now if we assume that this wave function has finite support, and also that the potential has finite support, and then we take the partial trace of the clock, so we're just left with what happens to the system, we see that for time before this time given here, that nothing happens to the system, and for all time after this slightly later time here, we've applied the unitary to it. Okay, so here's some example of some papers in the literature that use this result, but is there a problem with this? So does this really matter? And we argue that yes, and the infinite energy kind of disguises the true costs. And this goes back to what I was saying a minute ago, but the fact that that there's no degradation of the wave function and there's no back reaction on the clocks. So, for example, if you could now add many potentials rather than one, and in a very similar way get the clock to perform multiple unitaries on a system of interest, for example, and these could perform the unitaries corresponding to a quantum computation, to an algorithm. And then we see that without speeding up time, so without renormalizing time, we could just make the wave function arbitrarily narrow and do arbitrarily many unitaries in an arbitrarily short amount of time with no degradation at all to the wave function. In some sense, it will kind of trivialize computation because all computations could be done in an arbitrarily finite amount of time, regardless of how many gates you would have to apply. So there's that issue. It also, and the latter two we'll also touch on a bit later, how you could also imagine how if this wave function is flipping qubits at well-defined time, then you can have an arbitrary accurate clock as well. So it puts no limitations on how well we can measure time. And also, this is more from the quantum information literature, but there's this concept of embezzlement, and it also has implications here. So what is the solution? So now if you look at the wave function, now we had this wave function that initially we sampled at these discrete values. So to see its evolution, you just take this underlying continuous wave function, you do the rigid translation, and then you resample it again to get your points. And that is a good approximation. Because this error term, sorry, yes, I was just going to show here that the intuition up to this error term is that now, as time evolves, we just move around smoothly, and the only penalty for this is that now we have a slight, hopefully I can go back. Yeah, we have a slight spread, but it's not too much. And now the error decays is exponential decay in a dimension with this factor of pi over 4 in front, up to polynomial terms. Okay, so that's like a warm-up result we prove. And then the commutation relation, we also show that given the same definition of a time operator, that on the family of quantum states you get in this under the time evolution, that they do indeed satisfy the correct kind of canonical commutation relations up to this correction term, which again is exponentially smaller dimension. And this, by the way, proves a conjecture by Serge Massart and co-authors in this 2008 paper that they wrote. Okay, but this is kind of faster like the warm-up results. Now, the main result is the one that's really interesting for applications, is when we include the potential term. So here, this is kind of our main theme of the paper is that if you have this, so if you now define a potential which is analogous to the V of x, as written here, and we can define this in terms of more elementary potential V naught, which we assume to be a smooth function, which is 2 pi periodic. And we assume it to be periodic simply because now our clock is on a circle rather than on the line, right? So we want to have the same kind of symmetries. Then we prove this result here, which is the time evolution of our initial states, these Gaussian amplitude states, under the Hamiltonian of the clock in this potential term. If we look at the wave function, so to speak, so projecting onto this theta k basis, then we see that the first term here is what you would expect if you're mimicking this idealized behavior. So namely, we have the translation in space of the wave function. We have this factor of d over t naught now, it's just normalized times because the factor on the circle. But it's essentially the same thing. And now we have this integral over the potential, which again depends on the time. So this is analogous, but now we have the correction term. And of course, the important thing to all of this is this correction term. So what does it depend on and how does it scale? So this is what we proved that is equal to. So if for the moment assume b is constant, we see that because of the denominator in the exponential converges to 1 for large d, then we see that we recover the pi over 4 exponential decay in d for large d. And now I'll explain this b term. So the b term is defined as you can see below. So it's just some upper bound to the quantity where we take the kth derivative of our underlying potential, take its absolute value, look at the largest value in one period, raise that to 1 over k, and now take the supreme. Computation again, because in order to replicate the thought experiment I said earlier, where you just do your unitaries very, very quickly, but keeping the period of the clock the same, you would find that you'd need to make these potentials very, very steep, and hence the clock would kind of break down and it wouldn't implement later unitaries. So we see that it's kind of physical in a sense. Depending on the application, sometimes we'll want to parameterize this potential with the dimension d as well. So maybe this b can depend on the dimension, and then we may or may not get exponential decay depending on how we parameterize things. But there's a lot of freedom here, and this is useful for later results. So I will, yes. Okay, so I think I have to 20 plus 25, 20 to 25 past, so I have still some time. So I'll quickly go over the proof of this result. So first off, define this state here. So which is kind of the behavior we would expect if delta is t, right, for our wave function in the ideal case. And then the first two steps is to look at the evolution of this under some infinitesimal time step delta under the free Hamiltonian, so without the potential. And then we write this as in terms of a first term which is what we would have liked to. I'll give up because this mouse is not, it's not working very well. I was going to try and point to what I was saying, but hopefully you can follow me anyway. So we write in terms of what we would expect in idealized behavior plus a correction term. And then we bound in 2 norm this correction term up to delta squared, right? So this small time evolution squared. And then we do the same for the evolution with respect to the potential term. So we write down a term which is what we'd expect in an idealized case plus a correction term. And we see that actually in that time, in this case, it's only, there's no linear contribution, it's just delta squared. And then we have proven a little lemma that tells us that if we now iterate the process of applying the small evolution under H followed by a small time evolution under V and raise this all to the power M, then we can just iterate these two results to get the first term, which you see is time evolution now for M times delta, right, in both sides, which is kind of what we would hope for, plus some correction term. And then the little lemma tells us that the error on this error term is basically proportional to m times the sum of the errors in the intermediate terms, or at least it's upper bounded by that. And then the next part is quite forward. We just use the standard Trotter result that tells us that if we now let delta equal t divided by m, or at least proportional to that, and let m tends to infinity, then this left-hand side cell will converge to the dynamics we want, whereas the right-hand side now we have m times delta, so m cancels, and we just have t there, plus the correction term, which now, if we just take this limit on the right-hand side, we see the only thing remaining, now I'm at the very bottom right-hand side of the slide, by the way, is that this error term is bounded by this a term, which, if you remember, is given up here for the evolution under Hamiltonian. So now the only job left is to bound this a term. So if you go through the math, you see that A is given by this expression here, so we forget for a moment these summation terms. The kind of important part here is that this is this Fourier transform, and this is the continuous Fourier transform, by the way. So it's the Fourier transform of this Gaussian wave packet with this exponential term, which we can write out in full like this. And now the trick, and remember down here on the bottom of the slide, I show you what we want to prove. That's our aim, right? That absolute value of A is upper bounded by this quantity here, so that's where we're going. So now the trick is to integrate by parts n times. So we differentiate this term and integrate, integrate the last term. And now we take absolute values and use triangle inequalities, as you would kind of imagine. But it turns out that for any one n, this is not good enough. So if you do, you won't get the right bound. So it turns out that the useful thing is now to parameterize n to the number of times you take derivative before you take the absolute value in terms of the dimension and this sigma, the error. And when you do this, it turns out that the resulting problem is like a combinatorial problem. And I won't go into the details, but we use like Hermite polynomials, Faraday-Bruner's formula, and upper bounds on Bell numbers. And this upper bound on the Bell numbers was a central ingredient in this proof, otherwise we wouldn't have got the nice result, and this was only proved in 2010 by these people over here. So that's the overview of the proof. So now with, yes. Okay, so now with the time that's left, so I think I've been about 15 minutes, I have another, another 5-10 minutes, something like that. Okay, good. So I will now show some of the applications in quantum information theory. So I won't go in too much depth because of time constraints, but I'll give you an overview of 2 of the important results, and I'll show the others more briefly. So one kind of important application, as I alluded to earlier, is time. And you can think of like a wall clock as something that's that's emitting classical information at regular intervals, right? It's like tick, tick, tick. And we want to understand quantum versions of these and how well they can perform. Now, if we just consider idealized clock, the answer would be that we can do everything perfectly because there's no limitation. But now, because of this back reaction, it means that there's a limitation. It turns out that we can model clocks by a dynamical semigroup acting on a d-dimensional clock and some classical register, where the classical register at all times t is diagonal in a particular basis, and therefore, hence, I call it classical, and the state of this diagonal basis tells you the number of times your clock has ticked. And then you can ask questions of how accurate this is, and it turns out that although this is a dynamical semigroup, and the other result I showed you was Hamiltonian evolution, it's very useful because that result also holds when this potential is complex and not necessarily real. Anyway, I won't go into details, but it's exactly what you need to solve this problem. And we prove using that result that we have this measure of accuracy, which is how many times can your clock tick until the last tick has a standard deviation which is equal to the mean time between ticks, or in other words, how many times can your clock tick before the ticks become so inaccurate that it's useful. And it turns out that using this quasi-ideal clock, it's lower bounded by the dimension squared of the clock. And this comes from this exponential bound now, but now you see it's like it would be like 1 over a d squared, but the 1 over d squared comes from that exponential decay, but parameterizing the potential, so it depends on the dimension in such a way that you only get a 1 over d squared rather than an exponential small error. But anyway, that's what you get. And I didn't cite it here, unfortunately, but Yuxiang Yang and Colford also proved an upper bound that matches the lower bound. So they prove it's the best you can get. It's tight, using the construction from the 2019 paper. And this also outdoes the best classical clock or stochastic of the clock of dimension d, because there the optimal case is r equals d. So you can achieve that, but you can't do better. So it shows a quantum square root advantage. Okay. And I'd just like to say this is quite different from the results you get in standard metrology, because there the framework is that your system evolves and you measure, whereas here we want the system to output information by itself, to be autonomous. So just as a side remark. The second application I'll talk about is in the area of quantum control and catalysis. So here I'll go quite quickly, but the idea is that we have this quantum resource theory approach to thermodynamics, where the question is that if you have some thermal bath and you have some Hamiltonian that commutes with the local Hamiltonians of the system, what transformations are you allowed to go through? So if you start off some rho naught, what state rho 1 can you achieve? And here, as you see, I have this additional state called sigma, which we think of as a catalyst because it allows for the transformations you can reach to be a larger set. So it allows for more possibilities, and it's not degraded in this process because it has to be returned to the initial state. And then in this context, people realize that this is quite unstable in the sense that if you have a small error in this catalyst, so it's not quite returned to the initial state, and by that I mean that in trace distance, the error can go to 0 as the dimension of the catalyst goes to infinity. It turns out that you can ask, is this approximation okay? And it turns out that it's not. And the reason why is because there exists sigma and sigma epsilon, which satisfy this condition here, that that converge, in trace distance they converge to 0, but such that rho 1 can be any state. So it kind of trivializes thermodynamics. It's saying that you can go from any initial state to any final state if you even have just a tiny, tiny error on your catalyst. So this is why you have to be very careful in allowing these catalysts, because any small error and you can embezzle a lot from them. So how is this all relevant to clocks and the control I was telling you? Well, behind the scenes, there's this unitary that's being applied, and that has to come from some control device. And if you think of that as a resource too, it also should be returned to its initial state, because otherwise you can be embezzling from the control, you can kind of be cheating. So what you can do is you can now you can include the clock and allow this operation to be done autonomously. And now what you find is that you can think of the clock as a catalyst because it's returned to its initial state. If it was not interacting, there was no interaction term to do the unitary. But because it has to do this unitary, and because there is back reaction, because it's finite dimensional, it's not this perfect thing anymore, that back reaction means that the final state you get is not exactly the initial state. And what's worse, what makes it actually non-trivial is the fact that as the dimension of the clock, as we've seen, right, you have this exponential decay in the error as the clock gets large. So as the clock gets large in dimension, this error gets small. But we know from the above results from this 2015 paper, that by itself is not good enough. Because we know that even if the error goes to 0 as the clock gets very large, then you still may be embezzling. And that's precisely in the scenario we have these finite dimensional clocks. So what we proved, so Hideki and I proved in 2021 is that we proved a Converse embezzlement theorem, by which I mean that we say that if the rate in trace distance converges to 0 quicker than a certain rate with respect to the dimension, then the states that you can reach under this inexact catalysis is the same as if you had the exact catalysis. And then that's the first part. And then the second part is we prove the actual dynamics that you actually can generate physically using this quasi-ideal clock is good enough so that result implies that you can't embezzle. So we kind of save thermodynamics in the sense that now we show it can be done autonomously and without cheating, so to speak, without this embezzlement. Okay, so with a few minutes remaining, I just here leave up this last slide where I show some other applications. Some by myself, some by some with co-authors, and some by others as well, like this 2020 paper in Quantum Foundations. I also leave the conclusions here that basically what have we seen? That perfect clocks are unphysical in the sense they necessitate infinite energy. Finite clocks are physical but imperfect. And we bound these imperfections and show how the results are useful in quantum information theory. So with that, I think I finish, and thank you for listening.
Thank you, Misha. So are there some questions in the room?
So as far as I know, the most accurate existing clocks are atomic clocks. Mm-hmm. To which extent do they correspond to your model? That would be the first question. And the second question is, so these clocks need some particular states. They work on these Gaussian states. How can one prepare them?
Yes. Okay, so these are both very good questions. So the first thing I would say regarding the first part of the question is that here the bounds we get to timekeeping are kind of fundamental to quantum mechanics and not due to any kind of external noise, which, okay, you could argue whether noise is fundamental or not, but that's another issue. Like, we assume there's no noise. Now, at the present, the kind of the limiting factor in atomic clocks, in most exact clocks we have, are not due to any kind of fundamental quantum mechanical limitation, but more due to noise. So, in other words, there are atomic clocks in traps, in ion traps, and the external magnetic fields and things induce shifts in the energy levels, which you can think of as a noise. And hence, that's the kind of main cause of the inaccurate. So ours is kind of at a different level. There's another difference. That's one difference. I'll say the other difference as well, and this is something that they don't. If you look at the papers, they don't put any emphasis in, but is there in the background. I think is an important point. Is that in atomic clocks, we think of them as quantum, but there's also a classical counterpart, which is there's like a not very accurate classical clock, which tells you when to measure the quantum one and when to update that. So it's a kind of interplay between a classical clock that's not so accurate, but you can measure, that's like a ticking clock like the ones here, and more like a stopwatch, a quantum stopwatch that you can only measure, that it tells you the time when you happen to measure it, rather than automatically giving the time. And our model is more of the ticking clock. So I know Yujian Yang and Ralph, one of my co-authors on this paper, and I think Renato Rona has also worked on trying to find these kind of more hybrid models and push in that direction. That's something maybe they would, if Ralph Silver was here, he would be able to tell you more about, because I'm not an author of that. And sorry, I think that answers the first part of your question. Can you maybe remind me of the second part again? Sorry about that.
It was about the preparation of a Gaussian state.
Yes, okay, so yes, this is also a very good question. Yes, this is something, again, we haven't looked into. I presume Gaussian states are not too hard to prepare, in the sense they're relatively smooth and whatnot. Although having said that, I mean, here it turns out to get that d-squared scaling, you do have to make, as you make the dimension larger, to keep the accuracy increasing, you have to make it, the initial Gaussian, more and more peaked. And likewise with the potential term, you have to make it more and more peaked, as you would kind of intuitively imagine, I guess. So yeah, how to do this and what is the limitation from a quantum technology point of view and what we can do, I don't know. But those are also interesting questions and directions.
Okay, any other question? If not, then I think it's time to go to our second speaker. Thank you, Misha, again.
It's your mask. Oh,
Okay. And, so now we have a second talk by David Sutto. David made his undergraduate studies and his David made his undergraduate studies and his PhD at ETH, and he moved to IBM Zurich a year and a half ago. So he will present the second paper for this prize, Approximate Quantum Markov Chains.
Okay, does it work? Yes, okay. I hope you can hear me. So thanks a lot for the introduction. Of course, thanks a lot for the prize committee for awarding our result, which is joint work with these four wonderful collaborators like Marius Junge, Mark Wilde, Renato Renno, Andreas Winter. And you may wonder why I chose a different title than the title of the paper that was published in NS or in Poincaré. And the reason is that I wanted to make this talk a bit broader, such that the whole ICMP community, where not all of you are experts in quantum information theory, can maybe appreciate more sort of what was the basic problem that we were studying and that we were looking in. And then you can see that there are two, or maybe at least two approaches how one can interpret the result or how one can get to the result. One is more from a Markov chain perspective, and the other one is more from a relative entropy perspective. And we will go for the Markov chain setting. And as you will see, there's a big crowd of people that sort of were involved in this result, so it's not only the five of us. Okay, so let me start to motivate the problem. So suppose we live in a classical world and we have three random variables, a very simple setting. Then we say that they form a Markov chain in order x to y to z if conditioned on the middle one, so conditioned on y, x, and z are independent. So I think this is very obvious to all of you. And of course, one can make this mathematically formal in the green box here, that one says, well, okay, if they're condition independent, this means the conditional distribution of x and z given y, this factorizes, for example, or can use Bayes' theorem to rewrite it into this equation that you can see at the top. Now, okay, this is all trivial and good, and we information theorists, we like to sort of express these things about probabilities and the structure of probability theory. We like to express them in entropic formulas. So one alternative way to see that the distribution is a Markov chain is to compute the so-called conditional mutual information. So the conditional mutual information is defined at the top of the slide in gray. For those that don't know it, it's a sum and the difference of Shannon entropies. And what it means operationally is that it quantifies how much information does the x variable contain about the z variable if we know the y variable. the information in devices. And of course, if you're in a Markov chain setting, this means, as I explained before, condition on Y, the two outer ones, X and Z, are independent, so this conditional mutual information should be 0 in a Markov chain setting. And this is indeed the case. This is a very simple exercise that you can do in 1 or 2 lines to show that, okay, if you are in a Markov chain setting, as in the green formula, then the conditional mutual information actually vanishes. Well, that's good, because it gives us trust that this conditional mutual information is a sensible object, but one could also ask, is this robust? So what about distributions that have a conditional mutual information that is maybe not 0, but let's say small? And indeed, one can show that it is then robust. So suppose we have a joint distribution where the conditional mutual information is, let's say, epsilon, where epsilon is small, then one can show that such a distribution is close to a Markov chain distribution in terms of relative entropy. So this is the next and maybe the last information theoretic quantity, which is the relative entropy denoted with this D symbol. Some people may also know it as KL divergence, and it's defined again at the top, for those that don't know it. And so we can really say that in a classical world, we understand these Markov chains, and we also understand that they are robust in the sense that if you have a distribution that has a small conditional mutual information, such a distribution is always close to a perfect Markov chain in relative entropy. Now, okay, if this would be the whole story, then I wouldn't be here and I wouldn't have 30 minutes to give a talk. So, of course, what we tried to do in our work is to lift this to the quantum setting, where objects are not described by random variables, but they are described by density matrices. And then things become more delicate because there can be entanglement and there's complementarity, and this is what this talk is about. So I would like to tell you, okay, in which sense these classical insights about Markov chain, in which sense they translate to the quantum setting. Okay, and so this is the one very basic slide that just reminds you all about the differences between classical physics and quantum physics. So we all know we live in a quantum world, and quantum mechanics is arguably very different than classical physics. And the two major differences are, in my opinion, complementarity and entanglement. And I will not go into these two very fascinating phenomena, but we also see from a purely mathematical point of view that quantum mechanics is more delicate or more complicated, because classically, objects are described by distributions, but quantum objects are described, at least for quantum information theorists, are described by density matrices, which are positive definite matrices, and unlike distributions, which would be only diagonal matrices, these off-diagonal entries, they give rise to entanglement, they also give rise to complementarity, which is just the fact that matrices do not commute if they are not diagonal, for example. And this sometimes surprisingly complicates our very basic, rigorous understanding about very simple facts that we understand very well in classical theory or in classical physics. So take, for example, again, this conditional mutual information as I defined it in the previous slide, as the sum and difference of entropies. Now, if this is really an information measure that tells us how much information does X has about Y, X has about Z given Y, then we should be better able to prove that this quantity is non-negative for joint distributions. And indeed, classically, one can again prove this with a two-liner, but quantum mechanically, if I now consider the quantum conditional mutual information, where I take exactly the same definition, I just replace the Shannon entropy with the von Neumann entropy. If you don't know what the von Neumann entropy is, I will introduce it in the next slide. Then, and the operational meaning is the same, but if you want to prove that this quantum conditional mutual information is non-negative, this is surprisingly difficult. And it was open, I was told, for many years, until in the 70s, Elliot Lieb and Mary Beth Ruska came up with a quite complicated proof. And the proof was complicated, but the result was very deep, such that it became its own name. So it's today known as strong subadditivity of quantum entropy. And I would say arguably it's one of the key results in our field. So many results that we have today, they rely in some or the other way on this strong subadditivity. And as we will see, to understand quantum Markov chains, this strong subadditivity is very crucial. Okay. So, okay, I guess I can skip this slide. So this is the outline I already mentioned. So we would like to now translate the very first page where I told you a couple of things about classical Markov chains. We would like to translate them to the quantum setting, and we will see that there are certain subtleties showing up that we need to resolve and hopefully understand. And so, okay, the first thing is, again, of course, to define what we mean by a quantum Markov chain. Again, we have three systems, now denoted by A, B, and C. And unlike before, these are no longer classical systems, these are quantum systems. Quantum systems are described by density matrices, but intuitively we still want to express that this forms a quantum Markov chain if conditioned on the middle system, so conditioned on the B system, A and C should be independent. But now if you want to make this formal, then we run into a first small issue, because the concept of a conditional density matrix or conditioning on a quantum system, this is very delicate to do and should be avoided. I'm not aware of a sensible way to do that, so therefore we need to take another approach to define this rigorously. And the other approach is that if you again think, okay, what does it mean if A and C are independent conditioned on B? This means that suppose we lose the C system. Suppose we lose the C system and we want to reconstruct the C system by having access on the A and the B system. If we are in this Markov chain setting, then all the information A and B could have about C is already contained in the B system. So in other words, if we lose the C system, we can forget about the A system, we only need to act on the B system. And this is the whole idea of a Markov chain, right? That you at some point can forget about the past, so you don't need to carry around the whole past. Of course, Markov chains can consist of many more than just three subsystems. And so if you want to make this rigorous, I'm sure in the meantime you had already time to read the definition, so we can make this formal as follows. So suppose we are in a Markov chain setting, then there must exist a quantum channel, so we call this a recovery map. This is a completely positive trace-preserving map that maps from the B system to the BC system. And now we are in a Markov chain setting if and only if this equation 1 holds. So what does it mean? So it means exactly that if we lose the C system, so we have only here the marginal AB, then we can reconstruct the C system with this recovery map that only acts on the B system. So what is crucial is that we do not touch the A system. So this I symbol, capital I, this is the identity map that some people drop. If you read papers, sometimes it's not written, but it's crucial that the recovery map doesn't touch the A system. But of course, the A system needs to be there because A and B can be entangled in a quantum world. Okay, so this is the definition. Of course, classically, this is equivalent to the classical definition that we've seen before. This is needless to say. Now, this definition is a bit difficult to use in practice. So suppose somebody of you is an experimental physicist and prepares a tripartite state in the lab, and then he comes to me and asks, David, can you tell me, is it a Markov chain or not? Then I don't know how this recovery map maybe looks like, so it's maybe not so easy to convince somebody whether we have a Markov chain or not. Therefore, it was a nice surprise when Dennis Petz proved in the 80s the following theorem in blue. So he showed that a density matrix rho ABC is a Markov chain if and only if the conditional mutual information vanishes. So the same as classically. Of course, this is no longer a trivial statement as it is classically. This requires quite a complicated proof again. And Petz also proved that in case we are in a Markov chain setting, so if the conditional mutual information vanishes, then this recovery map that you see at the bottom of the slide always satisfies the Markov condition. This is equation 1. This is now nice because, again, if I have a density matrix, I just compute the conditional mutual information. This is just computing a couple of entropies. This is very easy to do, and if it vanishes, then I have a Markov chain. If it doesn't vanish, I don't have a Markov chain. Alternatively, I can use this very simple recovery map, which is called Petz recovery map, and look whether equation 1 holds or not. Now, again, as before, immediately after this theorem by Petz, people ask, well, this is nice, but is it robust? Because in practice, we would think that we have density matrices, rho ABC, that may have a conditional mutual information that is very small, but it is probably never exactly 0. So it's important to understand what happens with states that have a conditional mutual information that is small, and epsilon is small. And now following the classical intuition, it was sort of reasonable to conjecture again that such states, they are close to Markov chains. So this is this conjecture 1. So okay, kept it, or the conjecture was kept open, so it could be close in terms again of relative entropy, but it didn't really matter for the conjecture. So people were flexible and thought, okay, following the classical intuition, this should hold, but then it turned out to be surprisingly difficult to prove. So the community was struggling to prove it, and a couple years later, it was clear why they were struggling, because it was actually wrong. So there was a counterexample showing that you can have a family of states where the conditional the quantum conditional mutual information can be arbitrarily small by increasing the dimension of the subsystem. So this is this small d parameter. However, the distance, here now in trace distance, to any Markov chain is large, so it's constant. So this really kills the hope that conjecture 1 could be true. And again, classically, this is true. So the counterexample is a very quantum family of states. So it's a highly entangled family of states. So this was a surprise, and to still make sense of how to characterize states that have a small conditional mutual information, the community changed the conjecture. So they said, okay, maybe these states, they are not close to Markov chains, as we learned, but maybe they approximately satisfy the Markov condition. So this means the Markov condition was this equation 1 that you saw before. So it means that whenever we have a state that has a conditional mutual information that is small, there should exist some recovery map that approximately recovers the C system, right? And now at this point, it's very important that you understand that if conjecture 2 should be, or if there should be some hope that conjecture 2 can be correct, then we better make sure that it doesn't imply conjecture 1, right? Because this is incorrect, and this is not the case because this recovered state, so the term at the very right-hand side, this is not a Markov chain in the quantum case. So think about this. If this is unclear until the end, maybe approach me or ask. This is important. So conjecture 2 doesn't imply conjecture 1, so there's hope that this could be true. And indeed, it was shown, I think, by quite a groundbreaking result by Omar and Renato a couple of years back that this is indeed true, and then this was improved. This fuzzy-Renner result was improved afterwards by various people in the community, and also our result, which is presented here, is an improvement on this fuzzy-Renner result, and you can see it here in the theorem. So this looks a bit scary, but let's maybe take a couple of minutes to read the theorem, and let me try to explain why this may be interesting and why it importantly answers conjecture 2 in the positive way. So what does it tell us? That the theorem tells us that for any density matrix rho ABC, we have a lower bound for this quantum conditional mutual information in terms of the minus the logarithm of the fidelity between the original state, rho ABC, and this recovered state for a specific recovery map that we can, for the moment, forget. So now, maybe first point, I hope most of you are familiar with this fidelity term. This is this functional f, which is defined at the bottom. So this is a distance measure for density matrices that quantum information theory people like. So it's, okay, it's 1 if and only if the two arguments are the same, and it's 0 if they are orthogonal. And if you have density matrices, then it's between 0 and 1. So now, okay, let's have a look at this, the equation, the inequality in the theorem, and let's understand why it answers conjecture 2. So the theorem is correct for any density matrix. So in particular, if you have a density matrix where the conditional mutual information is epsilon, so very small, then we know that there must exist a recovery map, namely this recovery map that you can see here, such that this minus log fidelity term is even smaller. Now, minus log fidelity, if this is small, this means that the fidelity must be very large or very close to 1. So again, this means the fidelity is close to 1 if and only if the two arguments are close. So this now really quantifies the conjecture 2. It tells us whenever we have a state, so this is for the last time I hope, whenever we have a state that has a small conditional mutual information, then there's a recovery map that approximately recovers the state. And we can even see how the recovery map looks like. Maybe I comment on this in the next slide a bit. So here's the theorem again shifted to the top, such that we have some time to discuss a couple of things. So the first bullet is, I think, explained. So it tells us states that have a small conditional mutual information. These are approximate Markov chains. We can call them now safely like this because they approximately satisfy the Markov condition. Second, the recovery map that we see here is, I would say, it looks complicated, but it's actually a nice one because it has a couple of nice features or properties. So first, it's explicit, so we can write it down how it looks like. Secondly, it's universal. So what universal means is that it doesn't depend on the A system. So you can never see a subindex A on this system. So this is important because suppose you have two states, rho and sigma maybe, that have the same marginal on BC. So then this means the same recovery map works for both states. And this is important in certain applications. What is also worth noticing is that the theorem strengthens the strong subadditivity inequality from Elliott-Lieb that we saw at the beginning of the talk. So again, strong subadditivity tells us that the conditional mutual information is non-negative. Now, the theorem that we have above gives us a lower bound in terms of this minus log fidelity term, and because the fidelity is always between 0 and 1, we know that the lower bound is always non-negative. But of course, in practice, it can be positive. So it's really a strengthening of strong subadditivity, which is interesting because strong subadditivity is used in various places in our field. For example, to prove converse rates for channel capacities. And now we have an improved version of that that gives us hope to improve certain rates or certain results. Finally, I think I don't have time to go into the proof in detail, but I can say a couple of words that in the meantime we know several different proofs that follow different strategies, and one of the, I would say, more elegant proofs is one based on complex interpolation theory. So if you're interested in that, then have a look at the paper or approach me after the talk, and I'm happy to comment a bit on the proof. But it's not a simple proof, I would say, because even for strong subadditivity, which is somehow the more relaxing statement, we don't know a simple proof. So all of them have certain ingredients in the proof which are non-trivial, which are, for example, you cannot teach them in a lecture because they need some deep results, like monotonicity of certain matrix functionals or things like this. Okay, so instead of giving a proof, I would like to tell you why in a purely classical setting the theorem would be very simple, and therefore we cannot find such a result in a classical information theory book because there the statement is trivial. And from the proof why classically this is easy, you see where the difficulties show up in the quantum proof, and then, okay, we can discuss how the quantum proof works in detail offline. So what I mean by a classical state is that we just have a state that we can write down here in this basis where all the marginals commute pairwise, or they are simultaneously diagonalizable. And now I can remind myself what is the conditional mutual information. So it's defined via the sum and difference of entropies. This is the definition. And I can, if I want, I can plug this into one relative entropy. Again, this is by definition of the relative entropy. It's not clear whether this is smart to do because the price you pay is that the second argument in this relative entropy is quite a complicated matrix, right? It's the exponentials of sums of logarithms of density matrices. So it's the sum of Hermitian matrices, if you want to speak so. Now, because we are in a classical setting, everything commutes, right? Everything is diagonal. So therefore, we can just take this exponent of sums of matrices and relate it to the product of the individual exponentials. And then the logarithm and the exponential, they kill itself. You can rearrange terms. And if you rearrange them cleverly, everything commutes, so we can do that. Then we see that we have exactly the relative entropy between the state rho ABC and this recovered state, because this is, if you remember, this is exactly this Petz recovery map from before. So we have a perfectly nice statement, and okay, if you relax it a bit, this is standard, so the relative entropy can be relaxed or can be related to minus log fidelity, then we get the statement. But classically, we would have even a stronger statement because we could stop at the second last step at the relative entropy. And now you also see sort of the red part or the red step is the difficult one if you're in a quantum, in a non-commutative setting where we are not in a classical setting. So everything else would work in principle, but this middle step here doesn't work at all, right? And if we want to make this work, then we need to have sophisticated tools to relate exponentials of sums of matrices with the product of the individual exponentials. And so complex interpolation theory is one sophisticated tool that allows us to do that. Another one would be trace inequalities. So maybe some of you know the Golden-Thompson inequality that can also do these kind of things. But as I said, I will not go more into the proof, but I hope you see where the difficulties show up, and these are really quantum difficulties, so nothing for classical information theorists. Okay, so maybe I would like to spend 1 or 2 minutes to give you some history, and I would like to emphasize here that this was really not a one-man show of this set of authors that you've seen in the first slide, but this was a community effort to sort of achieve this result. And here's maybe a bit of history, so who contributed to this result and how it developed a bit. So I think it all started with the strong subadditivity of Lieb in the 70s. And then quite a bit later, Andreas Winter and Kay Lee, they came up with the conjecture that we now know today is a theorem. I think they were inspired by the classical proof that I showed you before, and they sort of came up with a conjecture underlined with numerics that this could be true. And I think they presented it in a small workshop in Canada. And that there was a famous set of notes which was then getting popular where people tried to prove it, and somehow was very difficult to prove it. Now, a couple of years later, there was this breakthrough by Renato and Omar where they proved a first version of this result. It had certain things that were not answered in this first proof, but this was the first fully formal proof that such a bound can be correct. So they couldn't quantify how the recovery map looks like. It was more an existence statement, but it was, I would say, one of the important steps that we, after this result, we really knew something like this is correct. And then only a couple of months later, their proof was very complicated based on Definetti type arguments. So only a few months later, there was a totally different proof discovered, which is based on an operational information processing principle called quantum state redistribution. But if you don't know this, never mind. But they were sort of developing a totally orthogonal proof, which gave us new insights how we can maybe improve this fuzzy Renner result. And then a couple of years later, one could find out that the recovery map, there's not only there exists a recovery map, but there exists a recovery map that is universal, so that doesn't depend on the A system. Then there was Mark Wilde's insight that we can use interpolation theory. That was a big help. And then there was the paper that I'm talking today about, where we could find this explicit recovery map with also proof based on interpolation theory. And afterwards, there was a proof based on Golden-Thompson. And also recently, there was the insight that this result generalizes to very abstract settings. So for those that attended Thomas Wittig's talk from before, so what I mean by abstract settings are these algebraic settings with complicated von Neumann algebras, which is important for the high energy physics people that start using this result now to make arguments about quantum field theories, where having results in these abstract settings is important for them, and this was not clear from the previous work whether this is true or not. So this was a new effort that is not so old. And I think there are still questions open that people try to solve there. Okay, so I think I have a couple of minutes left, so let me now try to relate this to this relative entropy, which is the title of our actual paper. But I think that the most important things you already, if you could follow until now, then you have you understood the most important thing. So what I mean by relative entropy, so there's another entropy inequality that is very closely related to strong subadditivity of quantum entropy, which is called the data processing inequality. So the data processing inequality tells us if you have the relative entropy in two states, rho and sigma, then if you apply a quantum channel, so this is a completely positive trace-preserving map to both arguments, then the relative entropy cannot increase. Some people also call this monotonicity of relative entropy, but this is an important inequality. And interestingly, it's really equivalent to strong subadditivity. So what do I mean by equivalent? I mean that if I know, somebody tells me, okay, here is strong subadditivity and here is a proof, then I can use this strong subadditivity result with only basic algebraic manipulations to derive the data processing inequality and also vice versa. If somebody gives me the data processing inequality, I can do very basic primary school arithmetics to sort of derive from the data processing inequality the strong subadditivity inequality. And therefore, it was, you can also ask this recovery business independent of this Markov chain setting, just as a question in terms of data processing inequality. So how does this go? So it was known, or it was proven by Petz that the following two statements are equivalent. So the question was, what do we need what kind of properties do we need on the channel such that the data processing inequality holds with equality? This was answered by Petz also a couple of years back. So he proved that the data processing inequality holds with equality if and only if there is a recovery map depending on the sigma state and the channel E that inverses the action of the channel on both inputs, so on sigma and on rho. And now, of course, the same question as we answered before for the Markov chain setting would be, okay, this is nice, but what if we have a channel that doesn't have data processing inequality with equality, but if the data processing inequality or the violation is small, or maybe better expressed, is what if this difference of the two relative entropies is not zero, but it's small? Now one can use the same proof as for the Markov chains to sort of answer the question. So here's the theorem again. So you see again a minus log fidelity term, but what it tells us, the theorem, is that this Petz result is robust in the sense that if we have a channel such that the difference of these two relative entropy terms is small, then there is a recovery map. We can express it, or we can write it down how it looks like, that has the two properties, so it inverts the action of the channel perfectly on the second state, on the sigma state, and it approximately inverts the action of the channel on the rho state, where the approximation quality is quantified with this log fidelity term. Again, because if the left-hand side of the inequality is small, then the fidelity must be very large, so this means the two arguments are very close. Right. Okay. So with this, I think I would like to conclude. So the take-home message is, I think, that if we have states that have a small conditional mutual information, we can safely call them approximate Markov chains because we know there's a recovery map, which is this rotated Petz recovery map that you saw before, that approximately reconstructs the C system by only acting on the B system. And we can use now these insights to also relate this to other type of entropy inequalities, not only strong subadditivity, we've seen just before the data processing inequality, but one can also use it to strengthen other entropy inequalities, like, for example, joint convexity of relative entropy or other things. But this is all in the paper, and if you have questions, then I'm happy to take them, and otherwise, thanks a lot for your attention.
Thank you. So, is there any question? Oh, yeah.
I have to admit that I don't know much about quantum Markov chains, but I'm very curious if you can say anything about such a Markov chain which is also stationary. I mean, is there a notion of stationarity for these Markov chains?
Yes, yes, that's a good question. So that okay, what we call a Markov chain is, I think, in the classical literature, some people call this a short Markov chain, right? We have only 3 random variables, and we just, what we call a Markov chain is just the fact that the 2 outer variables are in independent condition on the middle one. So, so this quantum Markov chain business has been, okay, the classical Markov chain community is, of course, much bigger and much larger, and there are much more abstract settings and longer Markov chains and stationary Markov chains. And I think most of them have been generalized to the quantum setting where the random variables are now density matrices. I'm not aware that like results similar to the one I presented for this very simple setting of this short Markov chain, that similar results have been derived for more abstract or more complicated Markov chain settings, but I know that some quantum people were studying more general concepts of quantum Markov chains. Yes.
I mean, maybe kind of a very simple analogy. Let's say, can you give some concrete conditions on your system such that if you only look at A and B, they have the same density matrix as B and C. That would kind of correspond to, I don't know, a baby.
Yes. That's a good question. Okay, I don't know. So what I learned in this Markov chain projects, or in these years I was thinking about, is that the quantum case can be surprisingly difficult even in very basic questions. So if you want to algebraically quantify, okay, what is the structure of these very simple Markov chains, this gets very soon or surprisingly complicated. So, and I think it's because of the more complicated mathematical structure that systems can be entangled, which classically you don't have. So I think I wouldn't be surprised if many of these questions similar to the one you asked, which look very basic, that they are surprisingly difficult to answer, and they may not be answered at all. But these are very important questions where maybe one can make progress. Sorry for the vague answer.
Any other question? Yes.
Yeah, thanks for the very nice talk. I was wondering, do you know or do you have any expectations about whether your bound is the sharpest possible? Or could there, for instance, also be lower bounds, like the relative entropy or something?
Yes, that's a very good question. So, okay, it's not the sharpest possible, this we already know. So on this history slide, there were improvements on this minus log fidelity bound. And you're perfectly right. So this log fidelity bound is a bit ugly because it's not strong enough to capture the classical result as we've seen in the proof. So the strongest bound that I know of is phrased in a relative entropy term, but we have to add certain measurements. So the strongest bound that we have is formulated in terms of a so-called measured relative entropy, which is strong enough to give you the classical result. If you plug in operators, they commute. But unfortunately, it's still open whether arguably the nicest result would be if you have just a relative entropy. So the same statement as classically, but just the quantum version thereof. This is still unknown whether this is correct. I would guess that it's probably not correct based on a proof that we developed based on Golden-Thomson that I couldn't present here, but we can chat offline. So I think there are some small arguments why it could not be true, but it's not ruled out with a rigorous counterexample or something like this. But okay, to answer your questions, there are better bounds than this log fidelity bound, but the nicest bound you would hope for this doesn't exist, and it may not be correct.
No more question? So I just have one question. Coming back to what Oya was asking, I personally know one definition of a quantum Markov chain, the one of Kummerer and Maassen, who is, I think, physically very appealing. So could you compare your definition with their definition?
Yes. Okay. Yes. Okay. I think they're related in the sense that the definition you are referring to is more general. So our one is just a very simple special case thereof. But it was okay. So far we only looked at this very simple setting of a short Markov chains with 3 systems, and I'm not sure. Okay, how much generalizes to the more complicated systems? But for sure, I would agree that this is a very interesting direction one should explore at some point.
Okay.
Yes.
Thank you. Well, thank you again. Okay, so we come to the third speaker of this afternoon, Johannes Bausch, who is online. So just to present him, so Johannes did his undergrad at Heidelberg, then master and PhD in Cambridge, and he is still in Cambridge now. So, Johannes, you have the power.
Thanks so much for the introduction. Yes, also first things, I'm very grateful for the award, also in the name of my co-authors, Toby Cubitt, who's now at UCL, and Maris Oswalds, who's now in Amsterdam. The award was for our paper on the complexity of translationally invariant spin chains with low local dimension. And I will try to explain the result and also highlight how we use the techniques developed within the result in various other results and how they relate and sit in the context of these types of results in history. So the first thing I want to do is, one second, I want to give you, I want to give you a brief overview over the construction and the result that we are proving. So I'll start with explaining what Feynman and Catalysis circular Hamiltonian mapping is. So this is a central technique that we use in our result. and it's relatively easy to explain. So imagine you start out with a quantum circuit like the following. So this circuit, let me see if I can get a laser pointer. Yes, the circuit has 3 gates. So you have a Hadamard gate here, you have a C0 gate, and another C0 gate. And you're starting out in 3, 0, and Scylla states. So what this circuit creates is a GH set state. And if we take the description of the circuit and write the following Hermitian operator, namely H is defined as an operator 1 to 2 tensored with the first unitary, so this would be the Hadamard gate, and then 2 flips to 3 tensored with the second unitary, so this would be the C0 gate. And then here you have the same thing again, you're flipping 3 to 4, tensor the third unitary gate. Then this operator has within as its ground state the uniform superposition over these so-called clock states, t going from 1 to 4, tensored with the state of the computation at that specific time step. So the space that this operator acts on is bipartite. The first one is clock space, which is where these operators act on. And the second one is simply the Hilbert space where the circuit acts on. Right. And then the ground state, as I just said, is essentially the time register entangled with whatever the computation does. Right. So in this setting, it would, for instance, be at time 1, you would have the all 0 state. At time 2, you would have 0, 0 plus, and so on. Right. So if you look at this Hamiltonian, and you add a few more terms, we can make this ground state energy, which in this setting would be 0, dependent on the outcome of the encoded computation. And again, without going into much detail, it's quite easy to see that, for instance, if I penalize the final state of the clock, so say at time 4, then I add a projector or some specific computational states down there, I can push up the energy, the ground state energy of this operator H, dependent on the outcome of this encoded computation. Right. So this is Feynman and Kitaev's circuit to Hamiltonian mapping. You start with a circuit, you end up with a Hamiltonian. The Hamiltonian encodes the computation, and you can add terms such that the ground state energy is dependent on the outcome of the encoded computation. So this is the construction in a nutshell. What do you do with this construction? Well, imagine you're a physicist in a lab and you have some physical system, like either given as a sample, or you have the explicit description of the system by having the local couplings of the Hamiltonian. And then an interesting question that you might ask is, does this system H have as its lowest eigenvalue, so as its ground state energy, an eigenstate with eigenvalue smaller than alpha, or is the smallest eigenvalue greater than beta? These bounds, alpha and beta, they're usually separated by 1 over polynomial in the size of the system. So in brief, what you want to know is the ground state energy of the system to polynomial precision. Now, based on Feynman and Kitaev's history state construction, Kitaev in 1999 proved that answering this question is difficult. Right, how difficult? I'll explain in a second. So in brief, it's difficult even if you had a quantum computer. So it's certainly difficult on a classical computer, and it will also be difficult on a quantum computer. And Kitaev proved this for systems with local dimension 2, such as the spins, with 5 local interactions and an arbitrary interaction graph. So these are not very physical. So historically, over the next few years, these results were improved. In 2006, Kempik, Kitaev, and Regev improved this to 2 local interactions. And then 2008, Oliveira Terhal had the first construction which brought the results to a realistic interaction geometry. So in this case, 2D and planar. And then in 2009, this was reduced to 1-dimensional systems. This, however, came with an increase in the local dimension to 12. the first really important result then, after Catalysis, was to prove the same for translationally invariant systems. So why is this important? Well, most systems in nature are translationally invariant in the sense that all the couplings are repeated in a translationally invariant fashion across the system. The price that Dr. Manirani paid for this is that the local dimension of the construction was enormous. So 10 to the 5, 10 to the 6. I don't think they to prove essentially the same result, but with local dimension 41. So we reduced the local dimension from 10 to the 6 to 41, so multiple orders of magnitude. And then a few years later, in joint work with Stephen Piddock, which was based essentially on the results derived in this Analysis Henry Poincaré paper, we proved it for a local dimension of 4, but the interaction structure was a bit more complicated. We showed this for 3-dimensional place-centered cubic crystal lattice. Right, so I said initially that these results are, the local Hamiltonian problem is hard for these settings. So there's a small difference between how hard this is. So the non-translationally invariant results are QMA hard. So this is hard even on the quantum computer, whereas the translationally invariant ones are QMAX hard. This is essentially an artifact of how you specify a translationally invariant system. So in brief, if you want the difference or the precision of the results to be 1 over polynomial in the system size, but the input of the system is a spin chain of length n in the translationally invariant setting, then the input to the computational problem is of size log n. So if I look at QMA, this means that the verifier that I'm encoding, or the computation that I'm encoding, has a runtime of poly in the input size, so poly log n, which you can show on the Hamiltonian side would result in a gap that's 1 over poly log in the system size. So that's too small. Whereas if you allow the verifier to run an exponential time, then the gap is just right. Okay, so much for the brief introduction. I now try to explain in a bit more detail how we exactly prove this result. So first, I'll show you the result explicitly formulated. So what we show is that the local Hamiltonian problem, so approximating the ground state energy, for a translationally invariant system coupled with neighboring nearest neighbor interactions and on a spin chain in 1 dimension, and with local dimension 41 is QMAX. And there are 3 main ingredients that we needed for this result. There's a new computational model called quantum ring machines, which we showed to be universal for quantum computation. There's a second computational problem called quantum Q system, computational model called quantum Q system, which we use to program the quantum ring machine. And then we derived results on unitary labeled graphs with unitary edge labels, which allowed us to relate these computational results to spectral properties of Hamiltonians. Great, so I'll start with quantum ring machines. A quantum ring machine, in brief, is a collection of spins that are arranged in a periodic cycle. And these spins can have B local dimensions. And what you also have is an operator S. And this operator S is just a unitary, which acts on 2 of these spins. And the quantum ring machine is then defined in the following way. You take this unitary S and you act cyclically on 2 neighboring spins on this spin chain. So it's depicted here pictorially as S applied to these 2 spins, and then you would increment the position of S and act on these 2, and on these 2, and so on. It's always the same unitary. And to raise this to a computational model, you start the computation in some initial configuration of the spins, and you define that the computation terminates in some final configuration. This can be a local configuration of a single spin or a global one. And this is defined in the same fashion as for Turing machines, for quantum Turing machines, and runtime and all the other properties are also defined in the same fashion. So what we showed about these quantum ring machines is that they are Turing universal. So this theorem reads quite complex, but it's relatively simple. You just say that if you have a promise problem in BQX, then there exists a quantum ring machine which also answers this problem. So in brief, if this promise problem is a yes, then with probability bigger than 2/3, the quantum ring machine in most polynomially many more steps terminates in a yes state, and the same holds true for no. Right, and the way we prove this is we simply encode or embed a BQX complete Turing machine into the system, into this quantum ring machine. Right, okay, so let's come to the quantum Q system side. So what we already showed is the computational model that's universal. What we now want to do is we want to program this quantum ring machine. And for this, it will be convenient to define a different computational model, namely quantum Q systems. So what is a Q system? So this was defined by a Norwegian mathematician named Tur. And it's a very simple computational model based on an alphabet. And then you have a set of length preserving rules, right? So you have this alphabet, and on substrings of a string, you define replacement rules. You can think of this as search and replace in your word processing program. Right, so this index set is finite, so you only allowed a finite number of replacement rules. And let me give you a very simple example. So if your alphabet is A, B, and C, and you have the following rules, replace C with B and AB with CC, and on strings of length 3, you get the following computational graph. So for instance, this string CAA would at most be translated to BAA, but then there's no further transitions possible. Whereas if you start with CCC, then there's a transition to the majority of all other strings. Right, so this is a very simple computational model. A quantum pure system is our extension of it. And it's a very simple extension. So you just add a few more symbols that you define to be quantum. It's a disjoint union. And you want that the rules leave strings invariant. So if a classical symbol is present, it preserves the classical symbol. If a quantum system is present, it preserves that the symbol has to be quantum. Right. And for every rule, you also attach a Hilbert space and a family of unitaries, such that the unitaries act on that many copies of the Hilbert space, as many as there are quantum symbols in the string in the replacement rule. This might sound complicated now, but let me give you an example again. So if your symbols are dash, star, and bar, that's the flat, and the quantum symbols in here are just the star. So dash and bar are classical. The Hilbert space is a qubit, and the replacement rule is single one, namely the star and dash is flipped, right? So star dash goes to dash star, and the quantum operation at that point in time is simply a Pauli X operation. And if I start in the following string, star, dash, and times and bar, I can see that at every point in time, I'm just moving the star over by one step. So at every point in time, I also have to act with this unitary on the Hilbert space. So if I start in qubit in state 1, then I will end up in state 1 if n is even, where n is the number of dashes in here, or I end up in 0 otherwise. So as a computational model, what this does is it decides whether n is even or not. Right. So with this very simple setup, we constructed a program called Turing's wheelbarrow. And Turing's wheelbarrow implements a BQX complete quantum ring machine and is programmed or computed as a two-local quantum Q system. Two-local in this context simply means all the replacement rules only act or include two symbols. So how do we go from Turing's wheelbarrow to saying anything about the spectrum of a Hermitian operator? This is where unitary labeled graphs come in. So this is also relatively simple. You start with a directed graph and a family of Hilbert spaces attached to all the edges of the graph. And then you also have a family of unitary to the vertices. The vertices carry Hilbert spaces, apologies. And the edges carry unitary operators. So as an example, this graph with 5 vertices carries the identity operation from 1 to 2, then from 2 to 3 there's U, and from 3 to 5 there's the unitary V and W, and then back to 2 with an identity operation. Now, if you look at the graph itself, you can look at, you can define the graph Laplacian as the difference of the degree matrix with the adjacency matrix. And you can write this as a sum of projectors on the difference of the vertices of the edges of the graph, right? So you're basically projecting on the antisymmetric subspace of the edges. Now, this is a graph Laplacian, and the ground state of such a graph Laplacian is the uniform superposition over all vertices. Now, if I add an additional Hilbert space into the mix, which is denoted here as this additional sum over a basis, and I'm just tensoring the edge labels with the spaces. And what I'm also doing is I'm acting with a unitary that's sitting on the edge E between A and B on this extra basis. Then this is a unitary labeled graph Hamiltonian, or also a history state Hamiltonian. So this is a more generic version of Feynman and Kitaev's circuit to Hamiltonian mapping. The Feynman and Kitaev one originally was just a linear graph where the unitaries just sat on the edges of this path graph. Whereas in this context, we have a graph that can branch. But what about branching though? Like what about here? You know, what happens with cycles and branching? Well, one of the major results in the paper revolved around precisely that. So we call a unitary label graph semi-classical if the product of unitaries around any loop is 1. Right? So what do I mean by this? I start at 2. I take the product of U, V, and W. And if that product of U, V, and W is the identity matrix, then this graph would be semi-classical. And then you can show the following very interesting result. If the graph, the unitary label graph is semi-classical, then you can analyze the spectrum of this graph very easily. Namely that there exists a unitary that partially diagonalizes this graph Laplacian, this unitary labeled graph Laplacian into copies of the classical graph Laplacian. And obviously then we can use all kinds of graph theory results on the graph Laplacian of this classical graph. With this, if the unitary labeled graph is semi-classical, we can perform spectral analysis of the resulting Hamiltonian. Right, so in our result, we also show that this quantum Q system is a local unitary labeled graph and hence can be embedded in a Hamiltonian quantum state. Right, with that, I come back to the main result, namely that we showed the local Hamiltonian problem for translationally invariant interactions is QMAX complete, even if its nearest neighbor translationally invariant interactions in the spin chain. Now, I said initially that these results are used in different contexts as well. One which I mentioned is that we also show this for place-centric cubic lattices. And this is very interesting because the result itself would be very difficult to derive if we did not have the notion of quantum Q systems and unitary level graphs. Because what we did in this context is we had replacement rules that we just very abstractly defined as what is happening between spins as a transition, as a computational transition. So we could simply say, well, we have this 3D lattice, we have spins in such and such a configuration, and then we just, you know, compute with these spins as if they were variables in a computer. And by using this notion of quantum Q systems, we can very easily skip all the explicit proofs of what this does to the spectrum of the resulting Hamiltonian. But beyond that, we Also used results that are related to this in some universality results and some undecidability and uncomputability results later on. Just as a very brief overview, in light of the short time we have left, the undecidability of the spectral gap result in 1D made use of some notion of unitary labeled graphs. And the result is quite easily explained as follows. Imagine you have this abstract size scale from small to large to thermodynamic limit. And you have a Hamiltonian with the spectrum that's depicted as follows. So you just draw lines where the spectrum is. And you assume that if you make the system bigger and bigger, the spectrum gets dense. But now the computation that you have encoded into this Hamiltonian is such that it could halt. And when it halts, you push up the energy of this Hamiltonian in a similar fashion to before. Now, if you add to this a trivial Hamiltonian, then with some additional machinery, you can show that this system becomes gapped at the halting threshold. And since you cannot tell in general whether a computation halts or not, this means that the existence of a spectral gap is also undecidable. We also used these quantum Q systems in a result proving that there exist universal translational invariant Hamiltonians. This was a joint result with Stephen Piddock. And also, as a very brief overview of the result, we know that the Heisenberg interaction with varying coupling strengths is universal. So what do I mean by this? If I have a 2D lattice and the couplings on the edges are simply the Heisenberg couplings, but such that the coupling strengths are numbers I can choose freely. Then within the low energy subspace, we know that this Hamiltonian can simulate any other Hamiltonian that you could come up in an efficient manner. Now, if you're in a translationally invariant setting, obviously you can't choose these couplings arbitrarily on a lattice. So what we did is we used these quantum Q systems to create a background field in a small area of this lattice. So we use the side length as input and then use that to transcribe onto a small area, this green area in the lattice, varying coupling strengths. And then we couple a Heisenberg interaction to this background field and universality that follows from perturbation theory. Now, as a last result, we showed very recently this year that it is even hard to approximate critical points of phase transitions, even if these phase transitions or phase diagrams are extremely simple. Right? So what do I mean by this? So we already knew that the existence of a spectral gap is uncomputable, but the phase diagrams, if you were to draw one, are extremely intricate. So what if you have the promise that these critical lines are very simple, kind of like we were motivated by the idea of water, which is very simple lines of criticality, then you cannot efficiently discriminate between the following two cases. So you have an order 1 region, which is in phase A, or an order 1 region, which is in phase B. And how hard is it? Well, we showed that it's even harder than QMA. It's hard for this class P to the QMAX, which essentially is the class of querying QMA oracle polynomial in many times. Right. Let me summarize the results. So the initial result with all the techniques was to show that estimating the ground state energy of 1D translationally invariant spin chains was hard. This was then further extended to 3D. We used these results in proving undecidability of the spectral gap in 1D translationally invariant spin systems, in uncomputability of phase diagrams, as I just noted, and then also in the existence of universal translationally invariant Hamiltonians. And I'll conclude the talk with a picture of Turing's wheelbarrow as we programmed it. The reason why we needed branching is very easy to see here. So all the blue lines are transitions that we define. And the way we programmed it is that there's multiple operations happening in parallel. So we have these ghosts that look like Pac-Man ghosts, and they perform one type of action, whereas there's also another type of head that runs in parallel and performs the actual computation. Right. So this was the motivation to look at history states with branching. Thanks again. If there's any questions now, I'm happy to take them.
Thank you, Johannes. Any question?
Hi, Johannes. It's David here. So what is the state of the art in the opposite direction? So if the number of dimension is sufficiently low, is it known that things are not hard, or is there any?
No, I think there's only results where you have some promises on the spectral gap of the system, right? So like in one dimension, I think if the spectral gap is open, there's an efficient method, which you're familiar with, to get the ground state energy and the ground state as well as an MPS. I'm not entirely sure if there's any results for frustration-free systems and very low local dimension. I'm assuming there is some for gapped and gaplessness, right? So these, I think David Goss said these Knabe type bounds, if the spectral gap closes at a certain rate, then the gap stays open. But I don't think there's a result on hardness of the ground state, because these Hamiltonians do have a closing gap, and they also are frustrated. So they don't really fall into any of the nice or easy settings. So I don't think there is any lower bounds. But I might be wrong. I mean, maybe someone else knows this better.
Any other question? So I have one Gaussian question. You mentioned the case of spin systems in 1D and 3D. What about 2D? Why?
Yeah, so this is interesting. So I had a master's student at ETH where we proved the same result for 2D. This is not yet published. We plan to do this. The local dimension in the result in 2D was not significantly better than in 3 dimensions. So than in 1 dimension, sorry. So you would expect that in 1 dimension, if the local dimension is 40, in 3 dimensions, the local dimension is 4, then in 2D, it would be sitting somewhere in the middle, right? That's very much expected. And it's quite easy to derive or construct systems in 2D or any other geometry with these kind of tools. But yeah, I would say it's at least local dimension 40, the same result holds, just copy the 1D construction over and over. It's probably better, like based on this this work with the master student, Artemi Burov from ETH, it looks like it's around 20 or 30 local dimension.
Thanks. No more questions? Then thank you, Johannes, again, and thanks to all
so much.
speakers of this afternoon.